Welcome to Calculus. Today we will investigate application of average rates of change and instantaneous rates of change to a free fall scenario, focusing on finding various time and velocity values within the parameters of the scenario. We've been working on finding average rates of change and instantaneous rates of change for abstract functions. And at this time, we need to look and see how this connects to free fall situations in the real world. So when we're talking about free fall, we're really thinking of an object in some fashion falling from a height towards the earth. And basically what we're defining as our x and our f of x is time and position, and then we'll use this idea of average instantaneous rates of change to define velocity. So we'll start here, we'll read the scenario, and then we'll come back up to this blank space to define average velocity and instantaneous velocity. So here we see if a ball is dropped from the top of the Empire State Building, which is 1,002 feet above the ground, the distance s in feet it falls after t seconds is s of t equals 16t squared. So as you can imagine, as we put in time values, we'll start with 0. There won't be any negative values because in terms of real life, we would only consider time as positive. And that would include all the time values up to the moment when that object or this ball strikes the ground at the base of the Empire State Building. So as I can see here, I am looking at part A. It says, what's the average velocity? And then part D, what is the velocity of the ball? That would be instantaneous velocity. So we need to define those before we get involved with the question. So let's define, first of all, what if I'm given some s at t, which is a position function, how would I define average velocity? So as you can see in the name, that really corresponds to what we've been looking at in terms of average rate of change. And so this would be the expression or the equation that does not involve the limit. It would correspond with our slope formula. So within the situation, we would say that we've got two different times, the time 1 and then time 0. So the time 0 is at the very beginning of the situation. And then time 1 is our value farther along as the object's falling. So the way I would write this is s at t1 minus s at t0 over time 1 minus time 0, or initial time. So that's for average velocity. And again, it would be between two different time values. Let's also define instantaneous velocity. Just like when we were talking about instantaneous rate of change, let me make sure I spell that right. This would be the equation that does involve the limit. Instantaneous velocity equals the limit. So here we're going to take the limit of the function as time approaches a given time 0. Now that could end up being 0. It could be some time within the parameters when the object's falling. So it doesn't necessarily have to be 0. Of this same function, now we modify it slightly because recall for this fraction, we actually put the function s of t minus s at t0, so that the position at that given time over t minus t0. So as you can see, these average velocity, instantaneous velocity really do look identical to our average rate of change, instantaneous rate of change. Just a word about wording. Instantaneous velocity is often referred to as simply velocity. If they're talking about average velocity, the writers will use the words average velocity. Well, let's take a look at the scenario. So we've already read the beginning of it there. We have this ball dropping from 1,200 feet and it's falling to the ground. The distance it's fallen is given by the function s of t equals 16t squared. And our first question here in part A is, what is the average velocity of the ball for the first 2 seconds? So I'm going to underline average velocity. And what that tells me is to pick up the average velocity formula. So average velocity, again, is the one without the limit. So this is going to be s at t1 minus s at t0 over t1 minus t0. So the interval that we'll consider is from the moment the ball was dropped, so that would be time at 0 seconds, until 2 seconds into its free fall. So we can label those values as t0 and t1. And what we really need to calculate for ourselves is what is the position at those 2 different times. So I'm going to create a very small table here, just with 2 input values, 2 outputs. So the times we'll consider are 0 and 2. And then what we want to calculate are the positions at those 2 different times. So our function is 16t squared. So for 0, you can think, how far has that ball fallen? Well, it's just not even been dropped yet, so 0 squared is 0 times 16 is 0. That's going to be our s at t0. I'll label that. And then our s at t1 will be how far it's fallen after 2 seconds. So that's 16 times 2 squared. 2 squared is 4 times 16 is going to be 64 feet. So we're ready to set up our average velocity fraction here. So I'm going to use the formula that we just wrote over here, but we'll actually plug in our numbers. So average velocity between 0 and 2 seconds is going to be s at t1, which is 64, minus the distance it's fallen at time 0 is 0, all divided by those 2 times, 2 minus 0. And that turns out to be 64 divided by 2, which is 32. We need to be careful to include units since this is a situation. So we are talking about velocity, and that would be feet per second. I can see the feet here, and the seconds are defined for our variable t. And we'll box that. So the average velocity between time 0 and time 2 seconds is 32 feet per second. Part B is an algebra question. How long does it take for the ball to hit the ground? What I'll do for this one is I'm going to bring the formula s of t equals 16t squared, but I know how far it actually needs to fall for it to hit the ground. That's the whole height of the Empire State Building. So I'm going to set that equation equal to 1,002. And then it's an algebra question because I just want to solve that quadratic. So for this quadratic, I don't need to really use quadratic formula because it's not got a b term, the linear part. So all I need to do is divide by 16, and that isolates this t squared. So I'll divide the right side by 16 as well. And what that gives me is t squared equals 1,002 over 16, which I could reduce to 501 over 8. And then to cancel the square, because I'm really just interested in time, I'd take the square root. And what that would give me is time equals plus or minus the square root of 501 over 8. And then I need to make an interpretive decision. I need to decide, do I need the positive time or the negative time? And in terms of a scenario, we wouldn't really be able to use this idea of negative time, so we'll just go with positive. And that has the approximate value of, if we calculated it out, 7.914 seconds. So not long for an object for this ball to travel from the top of the Empire State Building there in New York City to the ground level down on the sidewalk. It's just about 8 seconds, a little less than 8 seconds. So why do we calculate that? Well, the next question is really about average velocity of the ball during its whole fall. Part C says, what is the average velocity of the ball during the time it is falling? So in part C, I have to use that time that I calculated in part B to rerun average velocity on a different interval. So the interval we'll look at now is from 0 to 7.914 seconds. And again, what I need to calculate are the outputs. So I'm going to put a table, and my times again are these two extremes in the interval, 0 and 7.914. And what I want to calculate is what's S at t at 0 and 7.914. But it turns out I really don't have a lot to calculate. I can put in, again, 0 into the formula, 16 times t squared, so 0 squared, but that's 0 again. And then similarly, I could try to calculate 16 times 7.914 squared, but really, isn't that just the height of the Empire State Building, 1002? So I'm going to use those values again in the average velocity formula. We'll set it up again. So average velocity for my numerator, those are my two values in red there. The actual distance is fallen, so 1002 minus 0 over 7.914 minus 0. So definitely the zeros there cancel, and the approximate value of that is going to be 126.61. And if we think in terms of like, what are the units again? That's velocity, so feet per second. Let's just look at Desmos really quickly to investigate that graphically. So I want to just check and see what's that mean in terms of the scenario and the function on a graph. So let's share the screen and we'll go to Desmos. I want to graph the function itself. So I've got the plane scaled here. I'm going to type in S at t, but I need to do this in a Desmos friendly way. So I'll call it f of x equals 16x squared. So I'm using the variable x, but it's referring to time. So there's my function, and really I probably need to limit it to positive x value. So to do that, I'm going to put the curly bracket and say x is greater than or equal to 0. And that limits the domain there so that it really fits in the situation. Now, I'm interested in the y value of the height of the building. So I'm going to say also y equals 1002. Same here, I can probably limit this to x, got to have the curly bracket, greater than or equal to 0. So this point, and we can even check our value there, Desmos will give us the intersection. So it's saying 7.914. That's the time we calculated using average velocity, or using the algebra. So what we're saying with average velocity is what's the slope of the secant line between the initial point 0, 0 and that point of intersection when it hits the ground. Well, that would be this equation, y equals 126.61x. And again, if I just kind of limit that to the positive x values, x is greater than or equal to 0, you can see average velocity is really, it's the slope of the straight line, the secant from the initial condition to the end condition over that interval. I can see that that slope makes sure that it goes from the original 0.00 when the ball is falling to the point out there where it has fallen all the way to the ground. So we've used the graph there to kind of check our algebra. Well, let's take a look at the other questions we've got here. So we've got a couple questions here about average velocity, time it takes for the ball to hit the ground. And at this point, part D, we are asked, what is the velocity of the ball when it hits the ground? So remember, when we see the word velocity, really what we're considering that to be is instantaneous velocity. So on part D, we want to calculate the limit version of this fraction for the slope, instantaneous velocity. So let's set that up here. Instantaneous velocity will be the limit as our time approaches the time that we're interested in. So this is going to be the time when it hits the ground. So what I'm going to do, I'm going to substitute in right away that value. Now we again found that in part B there. So what I'm going to put for that time is it's at time approaches 7.914. So then I want to build this fraction. It's S at t minus S at t0 over t minus t0. So again, I put the generalized things there. Let's sub them out for the actual equation. So S at t, remember, is that 16t squared. And then S at t0, the distance it's fallen when it has hit the ground, is the height of the building. So that I'm going to put as 1002. And I can see that I'm kind of using my table values from here in that part C. And then in the denominator, t minus, so again, you leave the t as a variable, and then t0 is again 7.914. Now we want to use our strategies that are algebraic to simplify this limit. If I were just plugging stuff in, I would see the indeterminate form 0, 0, so direct substitution won't work initially. One thing I do need to notice, though, is that 1002, if I back up in my table here in part C, I could write that as 16 times 7.914 squared. So let's make that switch. So my next step, I'm going to call this the limit as time approaches 7.914 seconds, the time it takes for the ball to hit the ground. Won't change 16t squared, but I am going to change 1002 to 16 times 7.914 squared. Remember, our strategy in this situation is to cancel the denominator. So I'm looking for some way to factor that numerator to get a linear factor that matches this t minus 7.914. So to do that, I notice that I've got in the numerator two terms that share the factor of 16. So this is the limit as time approaches 7.914. And I'll factor that 16 to the side. So what's left is t minus parentheses 7.914 squared over t minus 7.914. And at that point, I need to just realize that this is the difference of two squares circled in green there. So that can be factored in the difference of two squares pattern. So this becomes the limit as t approaches 7.914. I had factored out 16, and then this will factor as t plus 7.914 times t minus 7.914. Again, I'm just using the difference of two squares factorization pattern from Algebra 1. the denominator is still that. And once I write it, I see now that I have an identical binomial above and below. And that's so nice. I can cancel. And what that leaves me with is a limit expression that I can now apply direct substitution to evaluate. So its limit as t approaches 7.914 of 16 times t plus 7.914. So notice my denominator has canceled. So I'm ready to evaluate the limit by direct substitution. So that's 16. I'm dropping the limit notation. Time is substituting in as 7.914 plus 7.914. And I could rewrite that as 16 times, in parentheses, 2 times 7.914, or 32 times 7.914. And for those who are familiar with physics, this 32 is the acceleration due to gravity. And that's in feet per second squared. If it were in meters, you'd expect that to be about 9.8. So in general, what this instantaneous rate of change, instantaneous velocity is giving us is the expression acceleration times time, which is one of the kinematics equations for the physics experts among us. Well, let's get our final answer here. So if I multiply that out, that gives me roughly the answer of 253.248. And again, the units that correspond with this would go with velocity, so feet per second. And we can just interpret that that ball is really moving at that point. At the moment it hits the ground after falling for 1,002 feet, it's speeding along. Watch out, don't be standing underneath it. So thank you for joining for this investigation of average rates of change in terms of average velocity and instantaneous rate of change in terms of instantaneous velocity, which we often just call velocity. Thank you for joining. I'll let you go work on your questions. See you soon.